Imagine standing beside a machine taller than a 20-story building, weighing more than 1,500 tons, yet capable of placing a 40-ton container with an accuracy measured in centimeters. You hear the deep hum of electric motors and the metallic echo of steel cables stretching high above the sea. Most people see these giants every day without ever asking where they come from. But here's what nobody tells you. Building a modern port container crane takes years, thousands of workers, and materials gathered from every corner of the planet. Think about this. A single ship-to-shore crane can lift more than 65 tons and move a container in less than 1 minute. Some cranes stretch over 80 meters above the water and reach across ships wider than a football field. The sounds never stop. Electric drives whine, brakes hiss, and massive wheels roll slowly along steel rails. And this is where it gets truly extraordinary. Before these machines ever touch a port, their journey begins deep underground. You are about to follow the hidden path from iron ore mines and copper deposits to one of the most complex machines humans have ever built. We will travel across Australia, Brazil, Chile, China, Sweden, and South Africa. You'll see steel glowing white-hot, robotic welders throwing showers of sparks, and engineers testing structures strong enough to survive hurricanes. What happens next surprised even experienced engineers. Everything starts with rocks buried beneath the earth. Most people never think about this, but nearly 90% of a container crane consists of steel. A single crane uses between 1,200 and 1,800 tons of structural steel. Much of that steel begins as iron ore extracted from the Pilbara region of Western Australia and the Carajás mines in northern Brazil. These mines produce ore with iron concentrations exceeding 65%. Massive haul trucks carrying 400 tons at a time crawl through clouds of red dust under scorching heat. After blasting and crushing, the ore travels thousands of kilometers by train to coastal ports. Bulk carriers then haul millions of tons toward steel mills in China, South Korea, and Europe. You can almost smell the diesel fumes and salty ocean air mixing together. Every ton of ore has already traveled farther than many people will in their entire lives. And that's only the beginning of the journey. But steel alone cannot create these giants. Copper from Chile's Escondida mine and Peru's Cerro Verde mine powers the electrical systems hidden inside every crane. High-purity copper reaches more than 99.9% purity after refining. Nearly 30 tons of copper wiring, motors, and cables may go into one crane. Without copper, those massive structures would stand silent and lifeless. South Africa and Kazakhstan provide chromium and manganese used to strengthen the steel. Nickel arriving from Indonesia adds corrosion resistance against years of salty sea air. Engineers carefully blend these alloys because even tiny percentages can change how the metal behaves. Most people never realize that a crane standing in California or Singapore carries minerals gathered from half the world. And each shipment depends on thousands of unseen workers. The steel cables perform one of the hardest jobs on the machine. Manufacturers produce them from high-carbon steel wire capable of withstanding forces exceeding 2,000 megapascals. Thousands of strands twist together into ropes stretching several kilometers in total length. When these cables move, they sing with a deep metallic vibration that echoes across the port. Their strength literally keeps thousands of containers from falling into the sea. Rubber tires and insulation materials begin their story in Southeast Asia, especially Thailand and Malaysia. Petroleum products from the Middle East become hydraulic fluids, paints, and protective coatings. Special marine paints shield the structure from corrosion for more than 25 years. The smell of fresh coatings fills fabrication halls long before the crane reaches the ocean. Every layer protects billions of dollars worth of cargo moving beneath it. But here's something shocking. Producing the raw materials for a single container crane generates more than 2,500 tons of carbon dioxide. Steel making alone accounts for nearly 70% of those emissions. Mining operations consume enormous amounts of water and energy every day. Engineers now search for greener steel and recycled metals to reduce that impact. Yet the world still needs these giants to keep global trade alive. Imagine thousands of tons of steel arriving at a factory where sparks fly day and night. Workers know that one mistake could affect a machine expected to operate for decades. Giant sections longer than houses wait to be transformed into towering structures that can survive typhoons and earthquakes. And this is where the real magic begins. Because what happens inside those factories feels almost impossible to believe. The moment those steel plates arrive at the factory, the scale becomes almost unbelievable. Some sections weigh more than 80 tons before a single cut takes place. Overhead cranes glide above the workshop while forklifts and self-propelled transporters move slowly between mountains of steel. You can hear steel clanging, warning alarms beeping, and the constant rumble of heavy machinery. But here's what nobody tells you. Every millimeter matters from this point forward. Computer-controlled plasma cutters begin the first operation. Their electric arcs reach temperatures above 25,000 degrees Celsius, or nearly 45,000 degrees Fahrenheit, hotter than the surface of the sun. The machines slice through steel plates up to 100 millimeters thick with cutting speeds around 1.5 meters per minute. Bright sparks explode across the floor, and the smell of hot metal fills the air. What happens next surprised even experienced engineers. Next, robotic drilling systems create thousands of holes for future connections. High-speed drills spin between 1,200 and 2,000 revolutions per minute, while coolant sprays continuously to prevent overheating. Each hole requires only a few seconds, but one crane may need more than 50,000 precision holes. The sharp scent of cutting fluid mixes with the sound of spinning machinery. Most people never think about this level of precision. The steel sections then enter giant bending presses that exert forces exceeding 1,000 tons. Hydraulic systems operate at pressures between 250 and 300 bar, shaping thick plates into curved components. Workers monitor every movement with laser measuring devices because even a tiny mistake could ruin weeks of work. You can actually feel the vibrations traveling through the floor as the press slowly bends the steel. And this is where the structure begins to take shape. Now comes one of the most spectacular stages. Robotic welding stations and skilled welders join hundreds of steel sections together. Electric arcs reach temperatures above 6,500 degrees Celsius, or nearly 11,700 degrees Fahrenheit. Every weld throws showers of bright sparks while the smell of heated metal and protective gases fills the workshop. Some weld seams stretch for several meters and require hours to complete. After welding, engineers perform stress relief treatments to reduce internal tension. Certain components spend several hours inside furnaces operating near 620 degrees Celsius, or about 1,148 degrees Fahrenheit. The heat changes the microscopic structure of the steel and improves durability. Massive orange-hot parts slowly cool under controlled conditions. What happens next determines whether these giants survive decades beside the sea. Huge assembly areas bring together components that resemble pieces of a skyscraper. Tower legs, booms, machinery houses, and support beams arrive one after another. Giant crawler cranes capable of lifting 600 tons carefully position each section. The sound of radios, engines, and steel chains creates a rhythm unlike anything else. Piece by piece, the giant begins to rise. Electric motors and gearboxes arrive next. Some hoist motors deliver more than 1,500 kilowatts of power, enough to supply hundreds of homes. Precision gears rotate smoothly while technicians install kilometers of copper wiring. You hear the clicks of tools and smell fresh lubricants inside the machinery room. Without these hidden systems, the crane would never move an inch. Thousands of sensors and cables connect to computerized control systems. Engineers carefully install cameras, anti-collision devices, and laser positioning equipment. Some systems process information hundreds of times every second to maintain perfect balance. Rows of blinking lights illuminate the interior like the cockpit of a spaceship. And this is where it gets truly extraordinary. Before painting, workers blast the steel surface with high-speed abrasive particles moving faster than 100 meters per second. The process removes rust and prepares the metal for protection against decades of salty air. Fine dust fills the chamber while giant ventilation systems roar overhead. Afterward, Several layers of marine coating create a shield nearly 400 microns thick. You can smell fresh paint long before the colors become visible. Final assembly can take several months. Some sections rise more than 80 meters above the ground, and workers climb endless staircases to inspect every connection. Wind whistles around the structure while hydraulic systems hiss and test motors begin to spin. For the first time, the giant looks exactly like the cranes you see at major ports around the world. But one mystery remains. How do engineers make sure a machine this enormous never fails when millions of dollars of cargo hang beneath it? Long before a finished crane reaches a port, engineers turn to technology that feels more like something from the future. Thousands of sensors, cameras, and computers monitor every stage of production. Artificial intelligence compares measurements against digital models accurate to fractions of a millimeter. You hear scanners buzzing and robotic systems moving with almost eerie precision. But here's what nobody tells you. Even the smartest machines still need human eyes. Robotic welding systems perform thousands of welds with incredible consistency. Their sensors measure arc stability and temperature hundreds of times every second. Laser tracking systems keep positioning accuracy within 0.5 millimeters, reducing the rejection rate to less than 2%. Bright flashes illuminate the workshop while cooling fans and hydraulic pumps create a constant mechanical rhythm. Most people never realize how much automation hides inside these factories. Massive CNC machining centers shape critical parts like wheel assemblies and gearbox housings. High-speed cutting tools spin between 3,000 and 8,000 revolutions per minute, while automatic coolant systems prevent overheating. Computer guidance maintains tolerances as tight as 50 microns, thinner than a human hair. The scent of cutting oil mixes with the sound of motors humming continuously. What happens next surprised even experienced engineers. Engineers use laser scanners to inspect every major structure. Millions of measurement points create a three-dimensional digital twin of the crane. Computers compare the model against design specifications and detect deviations smaller than 1 millimeter. Green laser beams sweep across the steel while technicians study glowing screens. A defect invisible to the naked eye has nowhere to hide. But some flaws hide deep inside the steel. To find them, technicians perform ultrasonic testing and magnetic particle inspections. High-frequency sound waves travel through the metal and reveal microscopic cracks before they become dangerous. You hear electronic pulses and see strange patterns appearing on display screens. Less than 1% of components fail these inspections, but every failure gets rejected immediately. International standards demand extraordinary reliability. Manufacturers follow ISO 9001 quality systems and comply with FEM and IEC standards used throughout the world. Engineers verify bolt torque, cable alignment, and electrical insulation hundreds of times during assembly. Some measurements allow tolerances no greater than 2 millimeters over structures longer than 100 meters. That level of precision feels almost impossible. Then comes one of the most dramatic moments. Engineers attach massive test weights equal to or even exceeding the crane's rated capacity. Some cranes lift loads approaching 80 tons while sensors monitor stress across hundreds of locations. Steel cables vibrate, motors roar, and the entire structure creaks under tremendous force. Most people would step back in fear, but the engineers watch calmly because they trust the numbers. Wind resistance testing pushes these giants even further. Engineers simulate hurricane-strength conditions exceeding 200 kilometers per hour. Computer models predict how the boom and tower will flex during extreme weather. Tiny strain gauges measure movement measured in fractions of a millimeter. What happens next determines whether the crane survives decades beside the ocean. And this is where human skill beats machines. Experienced weld inspectors can sometimes hear tiny imperfections hidden inside a weld simply from the sound made by a tapping hammer. Veteran technicians also recognize unusual vibrations that sensors might overlook. Decades of experience teach them things no computer can fully understand. Most people never think about the wisdom carried inside human hands. Modern ports increasingly rely on automation, and many new cranes operate remotely from control rooms located hundreds of meters away. Operators sit in air-conditioned cabins surrounded by screens and joystick controls, while cameras provide a perfect view. Artificial intelligence helps prevent collisions and optimizes every movement. The deep hum of servers replaces the noise of engines. And this is where it gets truly extraordinary. Some ports now move containers around the clock with almost no human presence on the docks. Cameras, radar systems, and machine learning algorithms coordinate dozens of cranes simultaneously. A single mistake could delay millions of dollars worth of cargo, so every system must work perfectly. Yet engineers continue searching for even smarter solutions. Because the next generation of container cranes may think, predict, and react faster than anyone imagined. Today, the world produces roughly 250 to 350 giant ship-to-shore container cranes every year. That may sound small, but each machine represents thousands of tons of steel and millions of engineering decisions. The global container crane market exceeds $8 billion annually and continues to grow as international trade expands. You can hear these giants working day and night at ports that never truly sleep. And this is where the numbers become almost unbelievable. China dominates the industry with nearly 55% of global production. South Korea follows with around 15%, while Germany, Japan, and Finland contribute significant shares through advanced engineering and specialized components. More than 300,000 people worldwide work directly or indirectly in container crane manufacturing, maintenance, and port operations. Most people never realize that these machines support almost every product sitting inside their homes. Without them, global trade would slow to a crawl. Think about this. Nearly 90% of world trade moves by sea. And container cranes serve as the gateway connecting ships to land. In the 1960s, cranes lifted only a fraction of what modern systems handle today. Early machines reached heights of around 30 meters, but today's giants stretch beyond 80 meters and can span ships carrying more than 24,000 containers. The transformation over the last 50 years feels almost like science fiction. Did you know that one modern container crane can move more than 40 containers every hour? That means a single machine can unload an entire skyscraper-sized cargo ship in just a few days. Another shocking fact involves height. Some cranes stand taller than the Statue of Liberty and weigh nearly twice as much as the Eiffel Tower's iron structure. What happens next surprised even veteran port workers. Here's another incredible fact. A single container crane may operate continuously for more than 30 years with proper maintenance. Some older cranes built decades ago still serve busy ports after millions of lifting cycles. Engineers constantly replace motors, cables, and control systems to keep these giants alive. The sounds of maintenance crews, grinders, and inspection tools never really stop. These machines age, but they rarely retire quietly. Did you know that future cranes may operate almost entirely without human intervention? Artificial intelligence, digital twins, and autonomous vehicles already work together at several advanced ports. Experts expect the market to exceed $12 billion within the next decade as smarter and greener systems emerge. Hydrogen power, renewable electricity, and predictive maintenance could reshape the industry forever. And this is where it gets truly extraordinary. Imagine walking through a port at sunrise. You hear the cry of seabirds, the low rumble of electric motors, and the metallic click of containers being lifted high above the docks. Most people see only steel and cables, but now you know the truth. These giants began as minerals buried beneath distant mountains and became masterpieces through fire, sweat, precision, and human imagination. But here's what nobody tells you. Every container they move carries a piece of this incredible story. The next time you stand near one of these giants, you'll never look at it the same way again. Behind every movement hides decades of engineering knowledge and the effort of thousands of people scattered across the world. From iron ore mines and blazing steel mills to robotic factories and intelligent control rooms, the journey remains nothing short of extraordinary. And even now, engineers continue pushing the limits of what these incredible machines can achieve. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.